Okay, so welcome to another episode, and today under the impedance, we'll be looking at the series circuit connection. The series circuit connections. And we understood that from this particular connection, or with impedance, there is the opposition to the flow of current in an AC circuit by the inductive element, the capacitive element, and by resistive elements. Okay. So now with this one, we first look at the series connection. So let's look at the series connection containing a resistor and an inductor. Okay, so you look at the series connection that is containing a resistor and an inductor. So you have something of this nature. You have the current I coming, which is connected to in series with a resistor and an inductor. So an inductor with inductive reactance XL, resistor with R, it has the voltage across, and then L. Okay. Okay. So we got the three. I want to do it so that you understand what I'm doing very well. Okay. So now from here, what we can see is that anytime there is a series connection between a resistor and an inductor, before you establish the fact that with them, current always lags the voltage. Current always lags the voltage. So now what happens is that with a resistor, they are all in phase. So if the current is in phase, this is how we draw their phase diagram. So now, this is the resistor, and this is the voltage across the inductor. So now, the inductor, with inductance, the current is always lagging the voltage by 90. So here, what we want to find is the resultant voltage over here. We want to find the resultant voltage over here. So let's say the voltage across the resistor is VR, and the voltage across this is VL. So if we do this, we want to find the resultant voltage and we find the phase angle between. But take note, because we are connected in series, for inductors, current is always lagging voltage. Okay, so now, what happens here is that you have to first find the magnitude V. So to find the magnitude V, which is equal to the VL, the magnitude of the VL plus the magnitude of the VR, which is equal to V squared, VL squared plus the V R squared. And this will give you V, which is equal to root of VL squared plus the V R squared. Okay. Now V here is the impedance. So V here is equal to IV. VR is the reactance, which is IR. And the VL here is equal to I, that is the current that is flowing, times the capacitive, the inductive reactance. Okay, so if that is the case, then we're having V, which is IZ, I times the impedance, which is equal to the root of VL here is what? IXL squared plus all squared plus IR all squared. So from here, we can factorize the I out. So if you factorize the I out, we are getting I, that is root of I into brackets, XL squared plus what? R squared. And when you do this, you can take this I out, the impedance. So to find the impedance when resistors are connected in series with an inductor, XL squared plus R squared. Okay. Now, since you have this, you can go on and find the angle. So the angle theta here, because if you join here, this place is now the value for the XL, and this is the R. This is the R. So the reactance here and the inductive reactance here. So now tan theta. So you can use, because tan inverse of the opposite, which is XL divided by R. And this is what will give us the angle or the phase angle when a resistor is connected to an inductor. Take note. One thing I'm supposed to do is that with this, the current will lag. So the current always lag, but will not be equal to what? 90 degrees. So now, when you are connected in series, the current will lag the voltage, but the current will not lag the voltage equal to 90 degrees because we are finding the impedance. So the resultant voltage, the current will lag, but it's not equal to 90 degrees. So take a look. Anytime you find the phase angle, the current is still lagging, but it will not be equal to 90 degrees. Okay. So the second one, I want to see the series connection. Containing a resistor and a capacitor. So you want to see the series connection containing a resistor and a capacitor. So now you have the current I, which is coming. This is our resistor with reactance and the voltage across, which is VR. And this is our capacitor with a voltage VC and our capacitive reactance, our voltage source. Okay. So now we have this. Now when you do this, what happens is that something you're supposed to take note that we said in capacitors, current is always leading voltage by 90. So if you want to draw a diagram, the reactance, that's the resistor, they are always in phase. So VR is always in phase. But current will always lead the voltage by 90. So therefore the VC will be here. We need the voltage. So the resultant voltage will be here, which is equal to IZ. And this one is equal to IXC. And this one is equal to IR. Okay. Now the angle here is the phase angle, what we'll be looking for. Okay. So now, since we have this now, we want to find the resultant voltage. So the resultant voltage is equal to VC squared, the magnitude of the VC squared plus the magnitude of the VR. So now V squared is equal to the VC squared plus VR squared. So now the V is simply what? The square root of the VC squared plus the VR squared. So now taking them, it's more or less like we did for the same place here. So we're getting IC is equal to root of ISC all squared plus IR all squared. So the V is here IC, ISC, and this. Okay. So when you do this, we want to find the impedance. So the impedance, when we have a resistor connected to the capacitor, is finally equal to the capacitive reactance, the square of the capacitive reactance, plus the square of the resistive reactance. So a simple Z is equal to square root of XC squared plus R squared. So unlike what is connected in series with an inductor, is XL squared plus R squared. What is it? Connected in series with the capacitor is XC squared plus what? R squared. And this is how we get it from. Okay. So now getting this, what do we do again? We have to find the angle. So we want to find the angle. This is the diagram. Here's the vein up. And this is the voltage, which gives us the IC. This is the IR. And when we put this side here, which is the vein C. So the angle is here as the phi. So now, if you want to find this side, this one gives us IC. Take the current there are always the same. So if you want to find this one, it is tan theta. Tan of the phi, that is the phase angle, is equal to opposite. So opposite, we are taking the XC divided by adjacent, which is what? The R. So therefore, the tan here becomes the tan inverse of the XC over the R. Okay. And this is how we find the phase angle when they are connected in series. Now the last thing we are doing today, but I always take note also that with this part, the current will lead. The current will lead as we've established that part. The current will lead this voltage, but not 90 degrees. It will not lead by 90 degrees. It will lead the resultant voltage, but it will not lead it by 90 degrees. It should take now. Now the last one is a series connection of the three of them, of the three elements. So a series connection containing the R, the L, and the C. So the resistor, the capacitor, and the inductor. So now we have a current I which is coming through a resistor with the voltage across it, through an inductor with its voltage, and also through a capacitor VC with its capacitor inductor. Okay, so now this is it. So this is across all of them. Now what can we say here? You realize that the resistance is always in phase. Okay. So if it is always in phase, then VR over here is always in phase, which is equal to IR. Now the voltage which we got from here is always pointing up because it always leads, but the current lags in inductors. So inductors, the VL is always up, which is equal to IXL. But when it comes to the capacitor, VC is always what? It's lagging the resistor. So the capacitor is always lagging, so it will come down here as VC, which is equal to what? IXC. Okay. So since you have this now, what we can do now here is that we can find the resultant voltage. So let's find the resultant voltage here. And the angle here will give us the phase angle. So to find the resultant voltage here, then the magnitude of the V will be equal to, obviously, the VR, magnitude of the VR plus the magnitude of the VR plus the magnitude of the VC. Okay, so now this is what you get in the start. But take note, now the VL and the VC, they are all in the y direction. And each time you draw a Cartesian plane, this plus, this minus. So if you want to find x very well, you can just subtract the plus from the minus and you get the magnitude of what you are looking for. So now the V square, and take note that the V here is IC. And this one I want to still find the impedance when the three of them are connected in series. So now the V square here becomes the VR squared plus each bracket. Here is the positive one, so VL minus the VC all squared. Okay. So now when you do this, the VR is simply what? The V is simply the root of the VR squared plus the VL minus VC all squared. I want you to take time and simplify this down. When you simplify this down by adding, inputting IC, which is the V equal to IC, so giving square root of this one is IR all squared plus IXL minus IXC all squared. When you do this, you realize that finally you'll be getting your Z to be root of R squared minus XL minus XC squared. Now, this does not always work, plus XL minus XC. It can always change because no matter this, you get to the negative. Whether it's negative or positive, you should come and still get a positive value. So sometimes when the capacity value is higher than this, you make this one forward. When the negative value is higher, you just put it there. So depending on what the values. Okay. So this will give what? The impedance when you are connected here. But how do you find the angle here? So now what happens here is that since you find this, the angle finally, this is the diagram. Okay. So here is the VR. This is our V, which is equal to IC, and this is equal to IR, and this here, the whole of this thing becomes VL minus VC, and that is equal to Finally, XL minus XC. Okay. So now since you're having this, so that is I, the current multiplying that. Okay. And this is the phase angle. So tan theta here will be equal to opposite, which is the XL minus XC divided by the adjacent, which is the R. So therefore, the far, tan of the far will be equal to, the far will be equal to tan inverse of XL minus XC all divided by R. And this is how we find the phase angle when there's a series connection between both three elements. Okay. There's no need to memorize how to calculate all of them or how to prove all of them. All you need to know is one. You need to know how to find the impedance here. That's the impedance here when it's a resistor and an inductor, and how to find its phase angle. When it's a resistor and a capacitor, how to find its impedance and the phase angle. And when the two of them are connected, how to find the impedance and the phase angle. Thank you very much for joining this class. And let's move on to the other class where we have some examples to solve. Bye.